Hello, welcome to Basics of Finite Element Analysis Part 2. Today is the last day of this course, and what we plan to do in this lecture is close the discussion on plane elasticity problem, and then after that, if we have time, we will make some general remarks and some important remarks in context of how to develop a good mesh. So, that is what we plan to do today. What we will do today is, so yesterday we had developed the relation at the element level for the entire plane elasticity problem. What we plan to do today is do a simple example and see how do we go around doing the assembly. So, consider a problem which looks something like this. So, this is the domain and I have broken it up into several elements. Okay. So, total number of elements I have here, this is 1, 2, 3, 4, 5, and I also have one element here, 7, 6. So, total number of 7 elements are there, and then my global degrees of freedom are 1, 2, 3, 4, 5, 6, 7 and 8. And then what are my boundary conditions? So, I will actually just oops. So, this is global degree of freedom 2. So, the boundary condition is that it is rigidly fixed here, it is also rigidly fixed here. So, this is node 4, it is also rigidly fixed here. Here it is fixed in the y direction. So, this is my x and this is my y direction, and at this thing also it is fixed in the y direction at node 3, and then on this surface I am having some traction in the normal direction. So, let us say this number is P0 and my local degrees of freedom are 1, 2, 3, 1, 2, 3, 1. So, you note that in every case I am putting my local degrees of freedom in counterclockwise direction. So, we have to be careful about that. 1, 2, 3. As long as it is counterclockwise, I am fine. I can start 1 from anywhere, but I have to just be counterclockwise. 1, 2, 3, 1, 2, 3. Let us write the connectivity matrix for this. So, it will be 1, 2, 3. So, the connectivity matrix will have how many rows? 7, because there are 7 elements. It will have 7 elements, 7 rows, and how many columns? 3, because the maximum number of nodes in any element is 3. So, there will be 3 columns. So, the first row corresponds to element number 1, and what are the global nodes? 1, 2 and 5. right. Second row corresponds to second element. The global nodes are 1, 5 and 4, and again we have to go in the right order, 1, 5 and 4. Third element corresponds to third row, so the numbers are 2, 3, 6. Fourth element 2, 6, 5. Fifth element 4, 5, 8. Sixth element is 4, 8, 7, and seventh element 5, 6, 8. So, this matrix will help us do the assembly. Second thing, total number of nodes at element level. How many nodes we have? 3, and total number, so element level each element has 3 nodes and total number of elements is 7. So, number of equations, each element will give us how many equations for plane elasticity problem? It will give us 6 equations. Each element has 3 nodes and all are triangles and each has 3 nodes. So, 6 equations for each element and there are 7 elements. So, total of 42, right, 7 6 to 42. 7 times 3 times 2 is equal to 42. Global level, once I have assembled number of equations, once I have done the assembly, how many nodes I am left with? How many nodes do I have? Once I have done the assembly, we have 8 and each node has 2 degrees of freedom. So, assembled number of equations is 16. So, where do all these other equations go? They get absorbed by continuity relations, right. For instance, node 1, so this is global node 1 is shared by 2 elements. So, this eliminates, so this is shared by, so elimination, how many equations get eliminated because of that? 2 minus 1 times 2 is equal to 2. Node 2 is shared by how many elements? 3 elements. So, how many equations get eliminated? 3 minus 1 times 2 is equal to 4. Node 3, how many elements it's sharing, are shared by it? It is shared by 1 element. So, 1 minus 1 times 2 is equal to 0. Node 4 is what? Node 4 is here. How many elements are sharing it? 3. So, how many equations get eliminated? 3 minus 1 times 2 equals 4. Node 5 is being shared by 5 elements, 1, 2, 3, 4, 5. So, it is 5 minus 1 times 2. Why am I multiplying it by 2? Because there are 2 degrees, two equations, right. So, that is why 5 minus 1 into 2 is 8. Node 6 is how many? 3. This is node 6, equation element 3, 4 and 7, right. So, it is 3 minus 1 times 2 equals 4. Node 7. Node 7 how much? One element uses it. So, 1 minus 1 times 2 is equal to 0, and node 8 3. So, 3 minus 1 times 2 equals 4. Add them up together. 2, 4, 6, 10, 18, 22, 26. 26. What is the difference? 42 minus 26 equals 16. Okay. So, we get 16 assembled equations because all these things are getting eliminated. Which degrees of freedom are getting eliminated? That you can see either from the picture or from this connectivity matrix. Okay. So, this is important to understand. So, the elimination process of variables is same, there is no difference. Now, we will very quickly see how do we assemble the elements, right. So, when we eliminate, and we also have to add up. When we are doing assembly, we also have to add up several equations, right. So, we will do one or two examples and get comfortable with it. So, let us find out. So, we know that the K matrix has 4 submatrices K11, K12, K21, K22. So, let us find out the global element K55 for K11 submatrix. You know, this is at assembly level. At assembled level, what is, how do we calculate this? It will be an addition of several element level stiffnesses. So, let us look at, so this is node 5, this is global node, this is also global node. In when once we have done assembly, we only worry about global nodes. So, node 5 is shared by how many elements? It is shared by 1, 2, 5, 7, 4. So, how many components it will have? It will have 5 components. Okay. So, it will be equal to, so I am using lower case for element level stiffness matrix. So, it will get one component from element number 1. So, let us call this, on this side I am putting element number. Then it will get another component from element number 2. Then it will get another component from element number 4. Then it will get another component from element number 5. Then it will get another component from element number 7. Yeah, 7. And what are the subscripts? So, this 1 1 corresponds to what? It corresponds to this submatrix. This corresponds to element number. And then it also should have a subscript. All these terms should have a subscript. So, for the first element, what does global node correspond to? Global node 5. It corresponds to 3. So, it is 3 3. Understood? For the second element, global node 5 corresponds to which element? So, it is 2 2. For the fourth element, global node 5 corresponds to node 3, 3 3. For the fifth element, global node 5 corresponds to, so it is 2 2. For the seventh element, global node 5 corresponds to 1, so it is 1 1. understood. So, you have to patiently do this and you will be able to do assembly in this way. We will do one more example, or I do not know, I think we have explained this sufficient number of times. So, let us try to find out global matrix, and let us say 1, 2, and the global nodes are 4, 5. So, this 4 and 5, it means that there is a line. That boundary is being shared by how many elements? It is being shared by 2 elements. So, there will be 2 components, right. The first component will come from which element? Element number 2. The second component will come from element number 5. What about these superscripts 1, 2? Do they change or they remain same? They remain same. And what about the subscripts? 4 global node in element 2 means 3, and 5 global node means node 2 in element 2. Similarly, for element 5, global node 4 means local node 1, and for element 5, global node 5 means local node 2. Okay. So, again the process of of assembly does not change fundamentally. The only thing the only additional thing is that we have this extra superscript and we have to track it, otherwise everything else remains same. So, if we can assemble it for single degree of freedom, as long as we maintain the superscripts 1, 1, 1, 2 and 3, same process works for assembly. So, I think this completes the discussion of this 2-dimensional finite plane elasticity problem, and this also brings us to the closure of this course. I think what I have captured in context of plane elasticity, you can use it, you can develop element level equations, you can assemble them, you know how to apply boundary conditions, and then you have to solve these. There is one small thing I would like to mention, that once we have done the assembly, I get a K matrix, then I get a U vector, right. So, this is the global assembly, the assembly of all the equations. Then I get a big M matrix which will have 4 sub matrices, and then I have a So, when I am trying to solve this, if problem is static, which means u double prime, u double dot and v double dot are 0, then I do not have to worry about these terms. In that case, I only need what? I only need boundary conditions. I do not worry about what are the initial conditions in the system, and there could be 4 sets of boundary conditions The first set of boundary condition is that on the entire boundary I know u and I know v, which means what do I know? Which type of variables? Primary variables I know, and I am specifying essential boundary conditions. The other condition could be that I know u at some places and I know t x at some other places. Sorry, Ty. Then I have a mixed situation. The other case could be I know V at some places and I know Tx at some places. So it could be either one of these sets, okay, one of these sets. At a particular node you cannot know both, either know u or you know traction. And the fourth condition could be that you know Tx and Ty. In this case you are going to specify the secondary variables and enforce natural boundary conditions. So these could be 4 different situations. So you have to implement these conditions in the force vector accordingly, and then once you implement this, then you have to solve the equation. For dynamic problem, you not only have to know the BCs, but you also have to know the initial conditions. And what are the initial conditions? That at time t is equal to 0, what is the value of u and v in the whole system, not at just one point, and also what are u dot and v dot. So once you know u and v and u dot and v dot, the boundary conditions you already apply, right? Then what do? You integrate it in time. See, we have already integrated it in x and y, that is how we got this stiffness matrix. But in time we start our solution from t is equal to 0 and then we go to t is equal to 1, t is equal to 2. So we march forward in time. And how do we march forward? We have developed a methodology for that. We had discussed it in the first finite element method using Newmark integration method, right. So you use these time integration methods, and for each iteration of time, for each step of time, you find out a solution. So there were couple of methods, but here because it is a second order differential equation in time. So this is if there was no time component, then this would be a set of algebraic equations. Now, but now this is a second order ODE, it is an ordinary differential equation in time. So that is why I need initial conditions, because when I integrate u twice, I will get 2 constants, and those 2 constants will be satisfied by these 2. We have to determine them, we have to use these 2 in sets of initial conditions. So we use an integration method and we keep on marching in time, and that is again a numerical integration approach, and that is how we solve this plane elasticity problem. And if you want to learn more details about it, please visit our first finite element course, all the details are there. So this brings us to the closure of this course, and what we have accomplished in this course are several things. First, in the first week we did a recap of whatever we did in FEA 1, part 1 of the course. Then we moved on to understanding how errors are computed and estimated, and we developed several measures of errors. Then we moved on to understand how numerical integration happens, right, using Gaussian quadrature and Newton-Cotes method. and that we developed all the details of it in context of 1D problems. And then after we had understood it, and then we moved on to solving 1D two-dimensional problem using a single variable, and in that context we spent a lot of time trying to formulate the problem, develop its weak form, develop finite element equations, learned how to do the assembly, learned how to apply the boundary conditions, and also do the post processing. And then in last 2 weeks we moved to some new sets of informations, and we covered how do we go around doing numerical integration in two-dimensional systems. And in two-dimensional systems you have quadrature points in 2 dimensions. If you go to 3-dimensional system, the same method applies, and you basically project those points in the z direction also, and you again do the same numerical integration scheme. So, the movement from or the transition from 2D to 3D is pretty straightforward. If you know how to do 2D, you can do 3D relatively easily. And then finally, we ended up solving or formulating the plane elasticity problem, which involves more than one variable and it is in 2 dimensions. So, I hope that this course has been fruitful and rewarding to you, and it was a pleasure interacting with you all. If you have any questions, please send us email, and also prepare for your final examinations well. Thank you very much and best wishes. Bye.